Yeah, so welcome to Ground Zero, and today we're going to do day four. We'll start with mask. So, what is masked attention, or we call it the causal attention? Why do we call it causal attention? Let us discuss that in detail. Okay, so let's say this is a matrix. Okay, I'm not writing everything, so here all my words will be there. Word one, word two, and so on. Okay, so it will be here this side, and let's say here it will be word one. This is the attention matrix we're drawing. Okay, so there are several kinds of marks we can do. So now let us discuss that in detail. So usually there are several masking like pad mask, or let's say a the pad mask is something which is different from what we do. Okay, there's something called a normal mask, but we are not going to discuss that. We're going to talk about the causal mask, or what do we call it, the don't look forward mask. Actually, look ahead mask or whatever. What does causal mean? The word causal means something that a function fx cannot depend on any function of fx plus n. Means what? The function of fx. Let's say if I have a function like this, fx equal to fx minus 1 plus 2. So this is a causal function because see, does not have any term where fx is it is x minus 1. It's not looking forward. It's not taking in any values from the future. So, but if I had a function like fx plus 1 plus 2, this would be a causal function. So what we do here is that, let's say, let me fill a random matrix. Okay, let's say 1, 2, 3, 4, 5, 6, 7, 8. This does not look like an attention matrix, but I'm talking about in general. So this is the matrix we have. So let's say this is word 1, word 2, word 3. And let's say if we have a word 1 here, word 2 here, and word 3 here. This is my attention matrix. I know the values are not like should not be like this, but yeah, let's just say. So the original transformer model that we use in attention is all you need is an auto-regressive model. What does an auto-regressive model means? It means it can only predict any data using the data from earlier. Means you cannot, like, let's say if I have a sentence, I have a toffee. So if I give you an input of I have a, you can't use the word toffee to guess the word toffee. You have to use the word have I and a for that. Okay. So like if we start like this, let's say for the first token will be start, right? So when I give start, the transformer should give me I. When I give start and I, the transformer should give me have. When I give it start, have and I, it should give me a. I give it start, I have a, it should give me a toffee. When I give it start, I have a toffee, it should end with end. So this is how the transformer should work. Okay. So that is why what happens is that we actually mask these values. So see, word 1 can see word 1, so it's okay. But word 2 cannot see word. So I will make this value minus infinity. The next value also minus infinity. Here, word 2 can see word 1, okay. Word 2 can see itself, okay. Word 2 can see word 3, no. So it should be minus infinity. So this is what I do. Okay. So since it is minus infinity, that means the chance of that value occurring at any time, right? It won't happen at all. So, so when we apply the softmax, so what is the softmax of minus infinity? This one will become 0. We apply softmax, this will become 0. So at the end when we will teach you feed forward, you will understand how we can get the probabilities at the end. And this is why we do this thing. So this system is causal because we are not using the future tokens. We are only using the earlier tokens and it's itself. This is how we use a masked self-attention for, which will first start with feed-forward networks. So feed-forward networks is basically your first, there's this, let me draw this horizontally. Wait. So first you have this linear layer and then you have a softmax layer. So this is your feed-forward network. So this is basically what does it do? What's the simple use case in a transformer thing? I'll link you a resource for linear, uh, how linear regression works out. in that case how this neural network here, feed forward neural network will work in this case. Okay, so what I am going to discuss is how does it help it in our transformer. Okay, so what it does is that we are getting a transformer output, whatever the transformer output is. Okay, the linear network first divides it into the n classes we began with. So let's say if we had words like, our vocabulary had four words, for example. Okay, I am, tree, cat. These were my vocabulary. So what my feed forward network will first do is that it will take in the inputs from the transformer, whatever the inputs that are coming from the transformer, and then it will map the inputs to four values. Okay, so these four values are of I am, tree, and cat in that order. Okay, I am, tree, cat. I'm writing this here. Okay. So whatever the values we got from this, right? Whatever the output is. So let's say this is I, this is am, this is tree, this is cat. So we will get some probabilities. So from that probabilities, we run it through a softmax function so that we can bring it to the so we can actually see which probability is the maximum. Okay. So we bring it here, bring it here, bring it here. And after the softmax, we get a set of probabilities. Now, whichever probability is the highest, let's say my probability comes out that this is the highest. The softmax of the tree is highest. Okay, so that means my next word is nothing but tree. So this is done at the end of the transformer. Okay, so what we did, we take all the inputs from the transformer, whatever dimension they come in, and we map it into a one into whatever how many our number of classes. It's basically a classification problem we are doing here. We are basic not directly a classification problem, but we are dividing it into this will become one into classes. How many classes we have here? Okay, and then we are actually mapping those classes. We are this one will also be one into classes. So after that is done. So what will happen is that we get the probabilities of each. Let's say tree has a probability of 0.96, so it's highest. So we get to know our next word. Okay, is tree. So what a transformer here doing essentially is next word prediction. So this is how the end of the transformer looks like. Okay. So with this, we finish our day 4, and on the next day, the final day, we will assemble the transformer. We will make the transformer. What we have taught you for the last 4 days are individual parts of the transformers, and we will now assemble them together to make the transformers finally.